Okay, hi everyone, welcome back. We're starting lecture 6 here, and what I've drawn are is the reaction that we left off with in the last lecture. So the reaction of acetic acid with triethylamine. And that reaction forms acetate and triethyl ammonium ion. Okay, and so we said before, this is an example of a reaction between a Bronsted acid and a Bronsted base. And the Bronsted acid is going to be the acetic acid. And the Bronsted base is going to be the triethylamine. Okay. The reason I redrew these is that I want to introduce two more terms, which is this idea of a conjugate acid or a conjugate base. Okay. And so what we say is that acetate is the conjugate base of acetic acid. And the triethyl ammonium ion is the conjugate acid of triethylamine. Okay, so we're introducing lots of terms here: Bronsted acid, Bronsted base. We talked about Lewis acids and bases. Now we've got the conjugate acids and bases. You sort of have to just learn these. Conjugate base is related to, or a base is related to its conjugate acid via transfer of a proton. Okay, and so when you're deciding sort of what is what, you want to look at the species of interest and ask the question, does it have an exchangeable proton or not? If it does, it's an acid, and then its conjugate base is the structure without that proton. Okay, if it doesn't, it's a base, and its conjugate acid is the same species with a proton. Okay, so conjugate is basically a way of quickly relating one species to another in acid-base reactions. Okay, and so, oh yeah, one more important thing is, just for completeness, I can put the arrows back in for that acid-base reaction. And so these types of transformations, acid-base reactions, are the bread and butter of organic chemistry. And they're under what we call thermodynamic control. So okay, and what thermodynamic control means here is that the system proceeds to the state of overall lowest energy. Okay, the reaction proceeds to favor either the products or the reactants, depending upon the relative energies of those species. And so Okay, and so we can generalize this to sort of a generic acid-base reaction. And for our acid, we're just going to draw HA, and we're going to ask the question, I put an acid in water, how much of it gets converted to A minus plus H3O plus. And so in this transformation, if I want to push electrons, I can have the lone pair on oxygen attack the proton on the acid, cleave the HA bond, and then that gets me to the products on the right. Okay. And so just to sort of give you a little more practice, this is the acid, of course, is an acid. The water is behaving as a base. And A minus is the conjugate base of HA. And H3O plus is the conjugate acid of water. Okay. And H3O plus comes up quite a bit because anytime you put any sort of acid into water, you're going to get some extent. This reaction is going to proceed to some extent. The degree to which it proceeds or does not proceed will depend on the relative stability of the products and the starting materials. But because this is very common, H3O plus has a special name, which we call the hydronium ion. Okay, it's essentially a proton bonded to water. Okay, and so one of the very important things that we want to know as organic chemists is where this equilibrium, how far does this reaction proceed or not proceed? And so what we can do is define an equilibrium constant for this reaction. And we can define that as Ka equals Keq, which is the equilibrium constant, which is defined as the concentration of products over the concentration of the starting acid. Okay. And large Ka values mean that the reaction proceeds very far to the right. Small Ka values, less than 1, mean that it favors the starting materials. Okay. And these Ka values can take the dynamic range, so to speak, of Ka values is very broad. And so in order to kind of get it onto a scale that we can easily talk about, we introduce the term pKa. And p is a function. It means minus log. So you can have p of virtually any number. The pKa equals minus the log, the natural log of Ka. Okay. And so here is the important thing that you need to just kind of commit to memory. And I'm the first to admit that this is very confusing. And it was difficult, at least for me, to, sort of internalize it. But stronger acids are going to have a lower pKa. Okay. And weaker acids are going to have a higher pKa value, okay? And so, go to the next slide here. So the Ka or the KEQ is going to favor loss of proton from the stronger acid. Okay, so let's work through an example and we can see how this plays out. All right, so we can consider an acid such as hydrogen cyanide. Reacting, for example, with methoxide anion. Okay, and so when you mix these two reagents, a Bronsted acid-base reaction occurs. Again, if I'd like to show the flow of electrons, I can draw a lone pair on oxygen attacking the hydrogen, NHCN, and push the electrons in the hydrogen-carbon bond down to carbon. And so what I end up with then is this species, which is an alcohol known as methanol. And CN minus, which is known as cyanide ion. Okay. And so given this reaction, we can very quickly predict which way it's going to proceed, if it's going to favor products or starting material. And the reason we can do that is that the pKa's of many different common acids are measured and widely available. And so the pKa of HCN is 9.4, and the pKa of methanol is 15.1, okay? And so we can go up to our definition, circle these, and say, all right, we know that the equilibrium constant is going to favor loss of a proton from the stronger acid, okay? Stronger acids have lower pKa values, okay? And so for this reaction, proton is transferred from HCN to methoxide. Okay. And so that's sort of, I can qualitatively describe how that's happening now, using just the pKa values of the acids. But we can actually calculate the KEQ for this reaction using the pKa's. And so the way we derive that, equilibrium constant is always concentration of products over the concentration of starting materials. Okay, and multiplied by concentration of hydronium. And so even HCN in water is going to be dissociated to some extent. And so there's going to be hydronium both in the starting materials and products. I put them in there for completeness. They obviously cancel each other out, but they're going to help us with the math. And so we can rewrite this then as like that, okay? And by introducing this hydronium ion term, what I've essentially done is defined the Kas for HCN times for HCN and methoxide. And these are going to be minus the log of the pKa's. And so this is going to be then 10 to the minus 9.4 times 1 over 10 to the minus 15.1. And if you do that math, it's 10 to the 5.7 equals KEQ. Okay, and so what does that tell me? It tells me that the reaction proceeds to about 10 to the 5th to favor the products of the reaction. So in other words, there's 10,000 molecules of methanol for every molecule of methoxide, approximately 10,000 at equilibrium, okay? And so we can use these pKa's to derive KEQs and then understand how far to the left or right each of these reactions is going to proceed, all right? And so, let's see. So let me perhaps generalize this a little bit for a Bronsted acid in water. So okay, so if we take some generic acid in water, we're going to use water as our solvent. Okay, we can say that the Ka equals KEQ, which equals products, so concentration of A minus, concentration of H3O plus, concentration of H2O, over concentration of HA, concentration of H2O, okay? And so the water in this reaction is taken as solvent, So we assume that the concentrations of solvent are not going to change. It's in very, very large excess, okay? Okay, and so we just cancel out those terms. And so the KEQ, again, is going to be, oops, let me go back. Oh, KEQ is the concentration of A minus times H3O plus divided by the concentration of HA, and then the pKa equals minus log Ka, which is going to be minus the log of products over starting material, okay? And so it's important to remember that the log of any number less than 1 is negative. Okay, and so as I start to increase the concentrations of product, right, and that quotient in this expression gets larger and larger, the pKa value is going to wind up being more and more positive. And so I'll give you another example here. So, or actually, you know what, let me stop here and then this is a good breaking point. We'll stop and pick up then in the next lecture. So.